Every time you use an AI chatbot or see one of those incredible AI images, it really does feel a bit like magic, doesn't it? Like this mysterious black box doing intelligent things.
It does feel that way.
But the reality, the sort of deep truth underneath it all is maybe a bit more mundane and, well, maybe more fragile. AI doesn't think. It calculates.
Exactly. And we're finding out that this calculation, even though it's incredibly fast, it's built on shaky foundations.
Yeah.
For so long, the focus was just faster chips, bigger data.
More.
Right. But what Edzai Svabwa argues in Mathematics of Disruption, and this is fascinating, is that the next big leap isn't going to come from engineering. It's theoretical. It's going to come from mathematics itself, pure math.
Okay, so that's the core of our deep dive today. We're digging into Svabwa's ideas, these sort of 9 mathematical areas he maps out. Areas that show where current AI is weak, but also where the future could be rebuilt.
Yeah, our mission really is to unpack that fragility, why our current system's brittle, and then explore these foundational pillars that could lead to AI that's genuinely resilient.
And crucially, why this shift in thinking towards math could be a massive opportunity, especially for places like South Africa, for the global South generally.
It's about moving from just using the tech to actually creating it, achieving a kind of technological sovereignty. That's the promise here.
And it boils down to that one powerful quote, doesn't it? Disruption won't come from faster chips. It will come from mathematics itself. So let's start where Svabwa starts, with what he calls the original sin of how computers do math.
Ah, yes, the original sin. It sounds dramatic, but it's about floating point arithmetic. This is the standard way computers handle decimal numbers.
The numbers with decimal points, basically.
Exactly. And to do it efficiently, computers make a kind of deal, a trade-off. They get a huge range of numbers they can represent, but they sacrifice infinite precision. It's a practical choice, but it means errors are inevitable. Tiny ones, but they're always there.
Okay, so tell us about the big consequence of that, the one that, breaks basic math class rules.
Right. This is the classic aha moment for anyone studying computer science. Inside a computer, because of these limits on precision and the rounding that happens, 0.1 plus 0.2.
Yeah.
Well, that doesn't quite equal 0.3.
Seriously. It's close, but not exact.
It's incredibly close, but not exact. A tiny fraction off. And this isn't just a one-off thing. This tiny error happens billions, trillions of times inside a neural network. It even messes up fundamental rules like associativity.
Meaning A plus B plus C isn't always the same as A plus B plus C.
Precisely, which mathematically should always hold true. But in the machine, it doesn't always.
Wow. Okay, so that connects to something I've always wondered about. When you use a chatbot, even if you set the randomness setting to 0, why do you still sometimes get slightly different answers? Or things that look like hallucinations? Is that really down to these tiny rounding errors?
It often is, yes. Or at least it's a major contributing factor. What seems like randomness, or maybe even creativity, can actually be the result of these small errors accumulating and interacting in complex ways.
And it gets worse because of how we engineer these systems for speed.
Exactly. Choices like using GPUs for massive parallel processing, doing lots of calculations at once, and something called batching.
Batching?
Yeah, it's like, imagine you're cooking vet Coke. Instead of frying one at a time, you throw a whole batch into the bot together to be faster, more efficient. AI does the same. It groups user questions or data points together to process them all at once on the GPU.
Okay, I get the analogy. Super efficient.
Yeah.
But how does that make the error problem worse?
Well, think about it. If your question gets put in a batch with slightly different neighbors this time compared to last time, the sequence of calculations, and therefore the way those tiny floating point errors interact, it changes slightly.
Because associativity is broken. The order matters.
The order matters. So the final result shifts, just a tiny bit maybe, but enough to give you a mathematically distinct output. It's non-deterministic, even with identical input and zero randomness requested. It's not magic, it's just messy math amplified by the need for speed.
Messy math. Okay. And that fragility, that chase for speed, leads us right into the next big challenge, the optimization bottleneck. You said training AI is basically an optimization problem.
Fundamentally, yes. Svabwa uses this great picture. Imagine training is like trying to find the lowest point in a really rugged mountain range, maybe the Drakensberg. That's the lost landscape. You want the point with the least error.
And the main tool we use is gradient descent. How does that work?
Gradient descent is essentially feeling the slope right where you're standing and taking a small step downhill. It's like hiking in thick fog. You can only see the ground right beneath your feet.
So it's effective locally, but maybe not globally.
Exactly. It's crude in that sense. The landscape is full of traps. You might step into a small dip, a local minimum, and think you found the bottom, but the real deep valley is over the next ridge. Or you get stuck on flat areas, saddle points.
And that's why engineers have developed these, Szabo calls them hacks. Things like atom or momentum.
Yeah, they're practical fixes. Momentum helps you sort of roll out of small dips. Atom adjusts your step size. They work, mostly, but here's the key. They don't come with mathematical guarantees that you've actually found the best possible solution, the global minimum.
Ah, okay. So this is where the mathematical disruption comes in again, finding better ways to navigate that landscape.
Precisely. Imagine mathematics that gives you more than just the local slope. Maybe second-order methods that understand the curvature of the landscape, like being able to see the shape of the hills around you, not just the ground underfoot. That could potentially guarantee finding the best solution, or at least find it much, much faster.
And if you can drastically cut training time and cost, that changes everything, doesn't it? How does that directly link to what you call technological sovereignty?
Well, think about it. Right now, training cutting-edge AI needs enormous computing power, huge server farms, millions of dollars worth of GPUs. It's a game only the biggest players can afford. But if the key becomes mathematical insight, mathematical elegance, rather than just brute force compute, suddenly, a clever startup in Johannesburg or Cape Town doesn't necessarily need massive capital investment to compete. Their advantage could be brain power, mathematical innovation.
So innovation is driven by local smarts, not just access to expensive imported hardware.
That's the idea. That's sovereignty. When you can build cutting-edge tech based on your own intellectual capital.
That's powerful. Okay, so we've talked about how the errors in calculation. Let's shift to the what. What is the AI actually learning? You mentioned it's like a mirror of correlations.
Yes. Current AI is incredibly good at spotting patterns, noticing that things tend to appear together in the data it was trained on. X happens, Y often happens around the same time.
Like maybe seeing lots of data where ambulances and accidents appear together?
Exactly, that's correlation. But it doesn't understand why. It doesn't understand cause and effect. That requires a different kind of mathematical reasoning, often framed using Pearl's calculus of interventions. What happens if we do something? What's the probability of Y if we actively intervene and change X, written as P(y)(x).
And current AI struggles with that do part.
Massively. And that's a huge problem when the world changes, when the patterns shift, what data scientists call distribution shift.
Like a pandemic changing traffic patterns.
Or sustained load shedding changing energy consumption patterns, or a drought changing water usage. An AI trained only on past correlations becomes useless, or even dangerous, when the underlying system dynamics change. It can't reason about interventions.
Which is exactly what you need for policy decisions, for managing complex systems.
Absolutely. South Africa, with its complex dynamic challenges, needs AI that can move beyond correlation to causal reasoning. How do we best allocate water during scarcity? How should the grid be managed during load shedding? That requires mathematically grounded causality.
Okay, let's move to another foundational idea, information theory. Szabo argues that learning is fundamentally about compression. That sounds counterintuitive, maybe. How is intelligence compression?
Think about it this way. Learning is about reducing uncertainty, reducing surprise. In information theory, surprise or uncertainty is measured by entropy, Hx. Training an AI model is essentially trying to build a model that is less surprised by the data it sees, minimizing what's called cross-entropy.
So it finds patterns to make the data less random, less surprising.
Precisely. And the ultimate expression of this is the minimum description length principle, or MDL. It basically says the best explanation, the best model for any given data is the one that provides the shortest description of that data.
The most compressed representation.
Exactly. Today's huge models are often incredibly bloated. They've memorized vast amounts of data, including redundancies and noise. They haven't truly compressed the essence. Future AI, informed by information theory, will need to pack light, find those truly concise, elegant representations.
And that focus on compression, on efficiency, that directly helps with accessibility in places like South Africa.
Hugely. If you can build smaller, smarter, more compressed models, they need less data, less computing power. They could potentially run directly on a cheap smartphone, offline.
So not just a big English chatbot in the cloud, but maybe an i6 HOSA grammar tutor that works anywhere. Or a tool to identify crop disease right there in the field, no network needed.
That's exactly the potential. Efficiency through mathematical elegance becomes the key to democratization and accessibility, overcoming limitations in data and connectivity.
Which brings us neatly to the structure of data itself. Geometry and topology, the city of shapes. Why is understanding the shape of data so important?
Because data rarely lives in a simple, flat Euclidean space like we imagine on graph paper. It usually exists on complex, curved surfaces mathematicians call these manifolds. Current AI often ignores this underlying geometry.
And what happens when you ignore the shape?
You distort the relationships within the data. Think about trying to represent the curved surface of the Earth on a flat map. You can do it, but you always introduce distortions. Greenland looks huge, distances get warped near the poles. Representing complex data flatly does something similar. It messes up the meaning captured in the data structure, the embeddings.
And this makes the AI brittle, vulnerable.
Yes, particularly to things like adversarial attacks. These often exploit tiny, almost imperceptible changes that push a data point across a decision boundary in that distorted, flattened space. A few changed pixels make a stop sign look like a speed limit sign to the AI.
Because the AI doesn't understand the true shape of stop signness.
In a sense, yes. Understanding the deeper structure, the topology things like the holes, loops, connected components in the data shape, that's key to building robust AI that generalizes better and isn't so easily fooled. We saw this with AlphaFold succeeding by respecting the 3D geometry of proteins. That has direct relevance for things like local drug discovery efforts.
Okay, fascinating. Let's quickly touch on the other mathematical pillars, Vivobo highlights. Game theory, the arena of agents. Why is that crucial?
Because AI often won't operate in isolation. Think about AI managing trading on the JSE, or coordinating traffic flow with self-driving cars and taxis, or balancing supply and demand on the energy grid. These are multi-agent systems.
Where the actions of one agent affect the outcomes for others.
Exactly. It's strategic interaction. AI needs the mathematics of game theory to navigate these complex scenarios to cooperate or compete effectively.
But traditional game theory, like Nash equilibrium, assumes everyone is perfectly rational, right? Which humans and maybe AI aren't.
That's a key challenge. Real-world systems operate under what's called bounded rationality. People and AIs make good enough decisions with limited information and processing power. Developing game theory for these realistic scenarios is critical for managing complex urban systems, resource allocation, all sorts of societal challenges.
Then there's category theory, the cathedral of categories. This sounds very abstract. How does it help build better AI?
Category theory is like a universal language for structure and relationships. Instead of focusing just on the objects, like data sets or models, it focuses on the connections, the arrows between them, and how these connections compose. Think about the GOT train map. Category theory isn't just about the stations. It's about the lines connecting them and how journeys are built by composing those lines.
So it's like structural engineering for AI systems, not just building blocks, but the blueprint for how they fit together robustly.
That's a great way to put it. It offers a principled way to design AI systems that are modular, more easily understood, potentially even formally verified or certified as correct. This moves us away from the current approach, which is often like patching together different bits of code with heuristics and hoping it works.
Towards systems we can actually trust in high-stakes situations.
Exactly.
And finally, the far horizon, the quantum garden, quantum probability for AI. Sounds like science fiction.
It's definitely future forward, but the mathematical concepts are being explored now. Classical probability deals with likelihoods based on frequencies. Quantum probability works differently, using things like amplitudes, superposition, where something can be in multiple states at once, and entanglement.
How could that possibly help AI?
Well, theoretically, quantum systems offer exponential representational power. A few quantum bits, or qubits, can represent vastly more information than classical bits, and quantum phenomena like tunneling could potentially allow optimization algorithms to find solutions dramatically faster than anything possible classically.
And this is where South Africa might have a unique edge.
Potentially, yes. Because of existing national investment in large-scale computation and data science, particularly around the Square Kilometre Array, SKA radio telescope project.
Which deals with absolutely massive complex data sets.
Right. There's already expertise and infrastructure being built that aligns well with the demands of future quantum computing and quantum AI research. It means South Africa could potentially be a pioneer here, not just a follower. This mathematical frontier could be more accessible than we think.
What an incredible overview. From tiny rounding errors to quantum superposition, let's try to pull it all together. Why is mastering these mathematical foundations, achieving this mathematical sovereignty, so vital for South Africa's technological future?
It really boils down to agency. If you only consume technology developed elsewhere, you're always subject to its limitations, its biases, its costs. You're adapting to tools built for other contexts.
You're a user, not a creator.
Exactly. But if you understand and master the underlying mathematics, you can innovate at the fundamental level. You can design systems tailored to local needs, local languages, local constraints. You start setting the rules, defining the architecture. That's true independence.
And the twist, as Vabo points out, is that some of South Africa's biggest challenges could actually be strategic advantages here.
Yes, absolutely. The country's rich multilingualism, that's a perfect, complex, natural laboratory for pushing the boundaries of natural language processing, of understanding linguistic geometry.
Load shedding, scarce data.
That forces the development of hyper-efficient, super-compressed AI, precisely the kind of AI needed across the developing world. It turns constraint into an innovation driver.
That's okay.
Accelerates quantum readiness. The unique, complex problems South Africa faces demand unique, mathematically sophisticated solutions that might have global relevance.
Which leads us to the final, crucial piece, the non-technical foundation, the Ubuntu AI vision.
Yeah.
What does that entail?
This is fundamental. Zvabo argues strongly that AI development, especially in a South African context, must be guided by the philosophy of Ubuntu. I am because we are.
Meaning
AI must be developed for collective benefit, not just profit or individual gain. It needs to be transparent, inclusive, genuinely serving all communities, all 11 official languages. It must uphold dignity. And critically, it must be sustainable, designed to work within real-world energy and data limitations.
So it's an ethical and practical framework guiding the technical development.
Precisely. It's a call to action. Invest seriously in mathematical education from school level upwards. Fund this kind of foundational AI research. Build diverse representative public data sets responsibly, and create regulations grounded in Ubuntu principles. It ensures the math serves the people.
It feels like that combination, the complex local challenges providing the need and Ubuntu providing the values, could create something really unique.
I think so. It could be a blueprint for a resilient, equitable AI framework, not just for South Africa, but potentially setting a standard for the global South and beyond. Responsible innovation driven by necessity and principle.
Well, this has been quite a journey. We've gone deep into the machine's hidden mathematical flaws, its fragility, but also its incredible potential if rebuilt on stronger foundations. We learned the real breakthroughs might not be in silicon, but in abstract thought.
That the consistency we see, or inconsistency, isn't magic, it's math. And the future lies in embracing things like compression, causality, geometry, composition.
Guided by deeper mathematical understanding.
The future is definitely mathematized, as Vabo puts it. But the choices about how we mathematize it, what values guide it, those remain deeply human choices. We saw the power that can be unlocked by aiming for wisdom and resilience, not just raw speed.
So maybe the final thought for you, our listener, is this. We've explored these potential mathematical foundations for a different kind of AI, one perhaps leading to technological sovereignty. As you think about AI's role in your world, what foundational principles, maybe the specific shape of your community's data, the game theory of your local economy, or perhaps that core idea of Ubuntu, what will you prioritize to ensure this powerful technology serves collective flourishing and not just narrow interests?